So today is 6.4a. And you might remember that yesterday we had this equation dy dt equals 0.69 times y. And this is actually the general form. Oh, after we solved this, what did we get? We got 2 to the t, yes. So we got y equals 2 to the t power. So if you graph 2 to the t, it looks like this. And it goes through the 0.38. Because 2 to the third is 8. So then I just want to explain what this slope equation says. The slope equation says that if you want to find the slope at a point, aka the slope of that line, right, you just have to take 0.69 times the y value. So in this case, it would be 0.69 times 8. So to find the slope of this line, you just take 0.69 times 8. Or if it was a different point, like 0, 1, if you wanted the slope there, you just have to take 0.69 times 1. So this is a specialized slope equation where the slope is just the y value times a number. So the general form for that is dy dx equals ky. So in this case, the k was 0.69, but the k could be any number, and then it would be a different graph, but a similar graph. It still would be an exponential. Okay, so this is the math symbol way to say it, that dy dx equals ky. But if you put it into words, the way to say it is the slope is proportional to the y value. In other words, to find the slope, you just take the y value times a number. So the mathematical symbol way to say it is dy dx equals ky, but translated into a sentence, you just say the slope is proportional to the y value. And what that means is, if you want to know the slope at the point, all you have to do is take the 8, the y value, and multiply it by the number. And then that tells you the slope at that point, the steepness of the curve. Okay, then the other thing that happened yesterday is we saw the technique of separation of variables. So I didn't write down what separation of variables was. We just did it once, and then I mentioned what it was called. But today I want to really nail down what separation of variables is. So why was this hard to solve? Because it had a y in it, right? So if this had been a t, it would have been easy to solve because we could have just taken the antiderivative. But the y there made it tougher. And so if you have a differential equation that has a y in it, that's what separation of variables is for. So separation of variables is used when you have a differential equation. It's used to solve a differential equation. That has the variable y in it. So the purpose of separation of variables is to deal with this type of tough problem, the differential equation that has the y in it. So today we're just going to work more on practicing separation of variables. So this one is dy dx equals negative 2xy squared. And we're trying to solve this. In other words, we're trying to find the original y equation. And we have some more information. Y equals 0.25 when x equals 1. Okay, so when you're trying to solve something like this, the first thing to do is to separate the variables. So I'm going to put the dx on this side. So it'll say dy equals negative 2xy squared dx. And then I'm going to divide the y squared to the other side. So that'll say 1 over y squared dy equals negative 2x dx. So I just did some algebra and put all the y's on the left and all the x's on the right. That's called separation of variables. Got the variables separated. And it's used on problems like this. Okay, then after you do that, you can take the antiderivative of both sides. So you just put an antiderivative symbol on that side and an antiderivative symbol on that side. So now let's start with this side. Antiderivative of that is, well, the negative 2 is just a constant, so it just stays. This is x to the first power, so you add 1. So it becomes x to the second power, and divide by the exponent. So that is the antiderivative of that. Now for this one, a lot of times people think ln. You can see why they would think ln, right? So this isn't the right answer, so don't write it down, but some people might say, hey, the ln of the absolute value of y squared. You see why that sort of makes sense? Okay, now let's take the derivative of this to check to see if it's the right antiderivative. It's not the right antiderivative. I've pretty much already told you that. So when I take the derivative of this, apparently I'm not going to get that. So you take the derivative of this, and you do get 1 over y squared, but then you have to times by 2y because of the chain rule, right? So the derivative of this is this, not this. So that's why that's not the right antiderivative. So ln only applies when it's y to the first power. If it's y to another power in the denominator, you don't do ln. Okay, so now I've talked a lot about what isn't right. So I need to talk about what is right, obviously. So 1 over y squared, another way to write that, is y to the negative 2 power. So if you see it like that, you just have to add 1 to negative 2. That gives you negative 1. And then divide by the exponent. So is everybody good with this antiderivative? Everybody good with this antiderivative? Now I'm leaving something out. What am I leaving out? Plus c, right? Remember, I could put a plus c on this side, and I could also put a plus c on this side. But then I could take this c and subtract it over to here and combine it with the other c. So usually we just write plus c on one side. Yeah?
Could you explain the antiderivative?
Sure. So another way to rewrite 1 over y squared is it's the same as y to the negative 2. And then once you get it to that form, it's easy to add 1 and divide by the exponent. Good. And it's a little bit confusing because sometimes people think I'm taking the antiderivative when I rewrite it. But I'm not. I'm just writing it in a different way and then doing the antiderivative. Good. Okay, so here's the stage I'm at. Now I pretty much have the answer. I just need to figure out what C is. And I also need to solve for Y. So to solve for Y, I'm going to multiply by -1 on both sides. So that'll be Y to the -1 power equals, this -2 divided by 2 is -1. But then if I divide by -1, it'll be +1. So that's just x squared. And then C divided by -1, or sorry, times by -1 is -C. So I just simplified a little bit and multiplied both sides by -1. Okay, now I'm going to rewrite this. That's 1 over y. And now I'm going to take the reciprocal of both sides. So flipping this side gives me y, and flipping that side gives me 1 over x squared minus c. So now I'm pretty close to having the correct answer. I just need to figure out what c is. I figured out what y equaled. Now I just need to figure out c. To figure out c, you use the point they gave us. You plug in 0.25 for y and 1 for x. So 0.25 equals 1 over 1 squared minus c. .25 is the same thing as 1/4. This is 1/4 equals 1 over 1 minus c. So then the 1 minus c has to equal 4 if those two fractions are going to be equal. So then you subtract the 1. So then you figure out that c is -3. So final answer is y equals 1 over x squared minus -3, so plus 3. Everybody good? Now, one thing we do need to talk about is the domain. So let's look at the differential equation. Are there any x's and y's that you can't plug in here? Yeah, there's not a problem at all, right? There's no division, so you'll never be dividing by 0. There's no square root, so you'd never be taking the square root of a negative, etc. There's no problems with this. So in the differential equation, dy dx is always defined. So we're going to make a comment about that. Dy dx is defined for all x's and y's. So that's just from looking at the differential equation. I could tell that there wasn't anything that I couldn't put in for x, and there wasn't something I couldn't put in for y either. Okay, how about the final equation, the y equals? Is there a problem there? There is division, right? So that could cause a problem. But x squared plus 3 can't ever be 0. Because the smallest x squared could be is 0. And then if you add 3 to it, it's going to be 3. So we're never going to be dividing by 0. So the final y is defined for all x's as well. So y is defined for all x's. And so the domain is negative infinity to infinity. But you had to look at both of these pieces of information to find that out. Both the differential equation and the y equation helped you realize that everything is just fine in both cases. We'll see an example where something does go awry. It's coming up, example 2. But you have to think about this. For 2 reasons. The directions say you're supposed to think about it, so that's why I'm focusing on it, so that you're not confused by the directions on the homework. But the real reason is that you should always check to make sure there's not a domain problem. Okay, for example 2, we've got dy dx equals y over 2x. And we're going to solve this, which means find the original y equation. And in order to do that, we need an initial value, but I'll talk about that later. Okay, so first of all, is there ever a problem here? Yeah, when x is 0, there's a problem. So just make a note that dy dx is undefined when x equals 0. Now, we're not sure what that means at this point. We do know that there's no slope at 0, but that could mean that there's no point on the original graph, right? Because if there's no point there, there's no slope there. But it could also mean, could it mean that there's a point? Could the slope be undefined, yet still have a point on the graph? Yeah, it could happen. What does it look like? It could be a corner point or a cusp or a vertical tangent. So there's ways for the slope to be undefined without the function being undefined. But at this point, we don't know. It could be that there's not a point there, in which case there'd not be a slope. Or it could be there's a point with no slope, like a corner point, etc. You know what I'm trying to say. Okay, so we'll deal with that when we get the original y equation. We'll know what the situation is. But before we get there, I want us to make a slope field. Okay, so for the slope field, we're just going to pick a bunch of points, and that means put a bunch of tick marks down that represent how steep the graph is there. And we know how steep the graph is because we can use this formula for the slope. All right, so let's start at 1, 2. So you put a 1 in for x and a 2 in for y. So that'll be 2 divided by 2 times 1. So 2 divided by 2, which is 1. So the slope there is 1. So that means you need to draw a little tick mark that has a slope of 1. The slope of 1 is a 45-degree angle. So you don't have to be exact, but get as close to 45 as you can. Okay, now let's try 1, 1. That'll be 1/2. So just shallower than 1. Okay, now let's try 1, 0. The y is 0. So it'll be 0 divided by 2, so 0. So draw a little flat line there. Okay, how about 2, 3? So for 2, 3, it would be 3 divided by 4, so 3/4. So a little steeper than 1, not as steep as 1, but a little steeper than 1/2. So just do your best. So now let's do 3, 2. So that would be 3/4 as well. Wait a second, did I mess up 2, 3? Let's see. 2, 3 would be 3/4. So now I'm messing up. So 3, 2 would be 2/6, which would reduce to 1/3. So that's pretty shallow. Slope fields kind of get tedious, right? You just have to make a bunch of tick marks. So I'm going to try to save us from the tediousness, yet at the same time still make my point. So let's go out here to the point 9, 3. So the point 9, 3 would have a slope of 3/18, which is pretty not steep. It reduces to 1/6. Okay, unfortunately I need some down here too. So let's go with some negatives. -1, 2 would be 2 over -2, so it would be -1. And then -1, 1 would be -1/2. So isn't this just mirroring this? And isn't this just mirroring that? It's just a negative slope, but the same slope, just in the negative direction. So if you don't mind, I'm going to just kind of mirror those. Okay, so if we had a bunch more tick marks, that would be a complete slope field. But this is good enough to make my point for where I'm trying to go. So what's the purpose of a slope field? Shows you the steepnesses of the graph, right? But it's a way of solving. How can you get the solution to this from the slope field? You trace out the slope field, right? So for part B, now we're going to graph the particular solution that goes through 9, 3. So in order to graph the solution that goes through 9, 3, I just kind of have to trace out from here, right? And I think I have enough to convince you that it kind of looks like this. I'm not sure I have enough to convince you of that, but I'm trying to save us time and tediousness. It starts out kind of steep, but gets less steep. And the same thing happens over here, right? But I'm leaving out the 0 on purpose because I'm a little bit worried about 0 because I don't know. The slope is undefined there, right? So I don't know if it's undefined because this graph goes like this and there's an asymptote there maybe. Or, so then there's no point there? Or maybe there's like a corner, a cusp there. I can't really tell for sure at this point. So that's why I'm avoiding the middle ground there. Okay, so the slope field doesn't include these lines, right? But then when in part B, when I said graph the solution, that meant trace them out and get the y equals. So the purpose of the slope field is it's a way of solving this without taking the antiderivative. You can get a graph of the solution. You can see what y equals without having the equation for y. Okay, but we have a tool that will let us find the equation for y. So now we're going to solve and also 9,3 is going to be a point. So we're actually now going to find the equation for y. And if we do things right, and if we did things right here, the equation that we get should match up with this graph, right? Okay, so this is a differential equation. So to solve it, we need to take the antiderivative. Can we take the antiderivative straight up? No, because this has a y in it. So then what do? Separate the variables, right? Okay, so I'm going to cross multiply here and get 2x dy equals y dx. And then I'm going to divide the y over. And at the same time, I'm going to divide the 2x over. So it'll say 1 over y dy equals 1 over 2x dx. And before I go further and take the antiderivative, I'm going to rewrite this again as 1 over y dy equals 1/2 times 1 over x dx. Okay, so now I've got the variables separated. All the y's on the left, all the x's on the right. So now I can take the antiderivative of both sides. Antiderivative of 1 over y is the natural log of the absolute value of y. For this side, the 1/2 can just come out in front of the antiderivative, so it just carries down. And then the antiderivative of that is natural log of the absolute value of x. So this is 1/2 times the natural log of the absolute value of x. And then don't forget plus c. And usually we just put 1c on the right side. Okay, now I need to solve for y. So I need to get rid of the natural log, and I need to get rid of the absolute value. How do I get rid of natural log? Raise it up from e, right? So e to the natural log of the absolute value of y equals, actually I wanted to do something before I did that, but we can do it in the same step. What can I do with this 1/2 here? Yeah, I could put the 2 over here if I wanted. That would be legal. That's not what I'm thinking of. So let's say you have 3 times the natural log of 2. The 3 can be an exponent inside. So you can make that the natural log of 8. So this will be cleaner if I make this a 1/2 power inside. So this is e to the natural log of the absolute value of x to the 1/2 plus c. So don't let that confuse you. I did two things. I took this whole thing and raised it up for me, and then I took the 1/2 that was here and I made it an exponent on the x. Okay, now that's convenient because, yeah, sorry, Carter, go ahead.
Should the 1/2 be inside or outside of the absolute value?
Outside. Because this is not, yeah, it's whatever's in here to the power. Good. All right, so then this crosses out, right? That was our whole purpose for raising from e. So we got the absolute value of y. Now, how do you separate this out? When you have e to a power plus a power, what does that become? Yeah, it turns into multiplication, right? So it's e to the power times e to the c, right? It would be a very common mistake would be to put a plus here. But that's not correct, because if you have two things multiplied with the same base, then you add the exponents. It's like x to the 4th times x to the 2nd is x to the 6th, right? X to the 4 plus 2 power. So this would be e to the ln of x to the 1/2 plus c power. All right. So then that's convenient because then this e and that natural log cross out. So we've got the absolute value of y equals absolute value of x to the 1/2 times e to the c. Okay, now last thing I have to do is get rid of the absolute value. How do you get rid of absolute value? There's two possibilities, right? It could be positive or it could be negative. So we talked about that a little bit yesterday. If the absolute value of z is 12, then z could be 12 or z could be negative 12. So here, y could be this, or y could be negative this. So that was getting rid of the absolute value. So the last thing we need to do is figure out what c is. So we're going to use the 0.93 to figure that out. So when I plug a 9 in for x, I'm supposed to get a 3 out for y. Absolute value of 9 is 9. 9 to the 1/2 power is 3. So then you would divide the 3 to the other side. So e to the c is 1. So now we've got y equals absolute value of x to the 1/2 times 1. Let's see what works with this solution. So when I put a 9 in, I'm supposed to get a 3 out. Absolute value of 9 is 9. 9 to the 1/2 is 3. Times negative 1 is negative 3. So then e to the c is negative 1. that's impossible. You can't take e to a power and get -1. So that means this option is out. Now that happened yesterday too, right? The negative option is the one that got crossed out. Don't think that'll happen every time. Sometimes this one will be the one that doesn't work. So that's why you have to check both of them.
Is it possible for both of them to work?
I think it's possible, but I don't like to use the word usually or never or always, but
Typically.
I think it's possible, yes, for both of them to work. I'm not sure that it would be a function, but I think it's possible that it could match the differential equation. Okay, so here's our final answer. Y equals absolute value of x to the 1/2. Another way to write that is y equals the absolute value of x square rooted, right? Now, if x is positive, this is just the square root of x. Does this look like the graph of square root of x? Yeah, it does. And then when x is negative, it's y equals the square root of the opposite of x, which is this graph. Now, in that function, is x allowed to be 0? Yeah, you can take the square root of 0. That's 0, right? So now we found out that 0, 0 is a point on this graph. And so we found out that what's happening is a corner point or a cusp. I'm actually not sure which it is. I think it's just a corner point, but that's not important. The deal is the graph connects there. So this is the full graph of y equals the square root of the absolute value of x. Yeah.
I'm confused on how it can be in quadrant 2.
Because if you plug, let's say you plug -4 in for x. The absolute value of -4 is 4, and the square root of 4 is 2.
Okay.
So you're right. For this graph, -4 is not allowed. But for this graph, -4 is allowed.
Okay.
And it gives you this other half. This would just be y equals the square root of x. This is the other half of y equals the square root of the absolute value of x. Good. Okay, so let's talk a little bit about domain now. Here, the domain is everything, right? So y is defined. Y is defined for all x's. So on the last, there was a problem, or there weren't any problems, right, with either differential equation or the final equation. Here, there was a problem with the differential equation, but there wasn't a problem with the final equation, and that's why there was a cusp, or a corner point. It's possible that there could be no problems with the differential equation, but there could be a problem with this. So you have to look at both of them. That's the point I'm trying to make, is you have to look at the differential equation, see if there are any problems there, and look at the final equation and see if there are any problems there. And then those pieces of information together help you see what's going on with the graph. Everybody doing okay? All right, that's all I got for today. Thank you for listening.
Do we have to label the domain?